Hi, physics. This is Mr. Janowski. This is chapter 6 and 7, homework 5, problem 3. And this one is a little different. There's a neat trick to this one. So, what have we got? Denise, whose mass is 60 kilograms, is going skiing down a hill with a 35-degree incline. So, that's going to make it weird. She's not going across level ground anymore. She's going downhill because it's skiing. That's how you ski, usually. The coefficient of kinetic friction between her skis and the snow is 0.150. So let's see what we're doing. I don't have the A's there, but step what are we looking for in part A? What is the normal force on the sled? So we want F, funny looking F, sub n is equal to question mark newtons. And then for part B, how fast will she accelerate? So we want her acceleration. So for part B, we want A is equal to question mark, and the units for acceleration are, of course, meters per second squared. Step 1, make a sketch. So remember, we're on a hill this time. It's a 35-degree incline. So we've got something that looks like this. And I'm going to say that that angle right there is 35 degrees. On this hill, we have Denise. She's standing like this. Great. She's skiing, so she's going this way. So here's the speed lines. She's got a mass. I'm going to leave her mass out of the sketch this time. There's a mu sub k. We've got that too. All right. Now, a couple of things are going on here. I'm going to kind of mix in some step 2 forces things into this idea. It's going to be a little different. You'll see why. So, first thing, which way is gravity going? Gravity's going straight down towards the center of the Earth because it's gravity, and gravity pulls you towards the center of the Earth. How about the normal force? Okay, well, normal means perpendicular. So the normal force is actually going perpendicular to the hill. The normal force in this case isn't going straight up. It's going like this. So F sub n is like that. How about the force of kinetic friction? Well, Denise is going this way. She's going down along the hill. Friction opposes the motion. So the force of kinetic friction would be going back along the hill like this. And finally, this is not an acceleration. I'll go with green. I'm sorry, acceleration is not a force. But which way is she accelerating? Well, she's skiing. So she's accelerating along the hill like this. So if I were to do my free body diagram, I'd have some problems here. I would have one pretty vector, f sub g, and then I would have two ugly vectors, f sub k and f sub n. So that wouldn't be cool. And also my acceleration would be an ugly vector. Because if I'm going, according to the normal way is, of course, all right, I'll leave it right there. X is straight sideways, y is straight up and down. According to that coordinate system, I've got lots of ugly vectors going on here and only one pretty vector, which is f sub g. So the trick to doing this kind of problem is get rid of this coordinate system and rotate it. So you want a coordinate system where x, new x, is going down perpendicular to the slope of the hill, and new y is perpendicular to that. So that is still a right angle, and this is, new y. That is our new coordinate system. That may seem weird if you've never done that with your coordinate system, because usually x means sideways, x means to the right, y means straight up. Like look down at your page, that's what it is. Turns out, as long as x and y are perpendicular to each other, math doesn't care if x is straight sideways or if it's down at that angle, and y, as long as y is perpendicular to x, everything's cool. So we've got that. So let me go a little bit further. I'll do it this way. So next step 2, free body diagram, of course. It's helpful, I think, to do these. You don't have to do it this way, but I think it's the clearest way to do it. The box is Denise. Draw the box at an angle, to match the Denise that we have at an angle. Because remember, again, in our thing, that is new x. Oop. and that is nu y. But yeah, so you draw your box, and Denise, yeah, she's at an angle. So what forces do we have here? Well, yeah, we've got the normal force. Okay, that's in the nu y direction. That's cool. F sub n. We've got a force of kinetic friction going back this way. I kind of got it, but it should be a little clearer. That F sub k is in like the new negative x direction. So it's back like that. And F sub g, of course, is still going straight for me to make my point here. F sub g is still going straight down. So in our new system, F sub g is actually the ugly vector. So we've got to figure some things out about it. I'm kind of bouncing all over the place. Here's the idea. Part of F sub g, Alice's weight, is holding Alice into the hill. So part of it is going this way. And part of it is making her go down the hill because that's how skiing works. I mean, at least types of skiing works. So yeah, basically, the part of the force that is holding Alice into the hill is in the negative y direction. So I'm going to call that, did I say Alice? It's Denise. I'm going to call this one F sub gy. I'm going to call this one F sub gx. This is a right angle. And what's this angle here? This angle is actually the same angle as this. This theta is 35 degrees. Well, so is this theta. Is 35 degrees. Yeah, it's confusing. I'll show you in class how that works. Anyhow, back to our step 2. Yeah, again, I'm all over the place here. Step 2, yeah, we've got to do a step 0 to our ugly vector because we don't like ugly vectors. So, step 0, all right, really what we've got, our ugly vector is this. F sub g, going straight up and down. It has 2 components. F sub gy and F sub gx. This is a right angle. And this angle here, theta equals 35 degrees. All right, so F sub g, let me just add this in. F sub g is equal to mg. All right, so let's label our sides here. F sub g, this is the longest side of our right triangle. So this is definitely the hypotenuse. That's the hypotenuse. F sub g y, that's actually the adjacent in this problem. Because our angle is right here. So F sub gy is the side that is, next to or adjacent to the angle. So that's that one. So this one is O. F sub gx is going to be O. Remember, so ka toa. All right. So F sub g, let me see if I can squeeze this all in right here. No, these Jamboards are too small. F sub gy, I want A, I know H, I know theta. F sub gy is going to be the cosine one in this case. So I'll do the math right up here. It's going to end up being F sub gy is equal to F sub g is equal to, I'm sorry, I'm lying to you. It's equal to F sub g times cosine theta. If you started with cosine is adjacent of our hypotenuse, you would end up here. F sub gy is equal to F sub g times cosine theta. Remember, F sub g is actually mg. So we're doing a lot of the same steps, but we're doing them kind of out of order in this problem. Mg cosine theta, which means F sub gy, I don't want that there, get out of there. F sub gy is going to be equal to, mass is 60 kilograms. G is 9.8 meters per second squared times cosine of 35 degrees. And we're going to end up with F sub gy is equal to, I've got 481.6. Actually, 41.66 newtons. F sub gx, I'll change colors. Maybe that'll make it a little bit easier. Is going to be equal to F sub g times sine theta, which is really mg times sine theta, which is really 60 kilograms times 9.8 meters per second squared times sine of 35 degrees. Do that math. F sub gx will end up being 60 times 9.8 times sine 35. And I've got 337.2629. All right, so we'll go with 337.26 newtons. All right, so what does that give us? F sub gy is really equal to 481.66 newtons. F sub gx is really equal to 337.26 newtons. All right, so I have those values. Now, of course, we go back and we do another step 2. So step 2, again, remember, we're doing it on the tilt here. So here's our new y. Here's our new x. Our free body diagram. You know, the box is now, Denise, tilted at an angle like that. So remember the normal force, that was already a pretty vector. F sub n like that, you know, pretty according to our new coordinate system here. F sub k was already a pretty vector. And now, instead of drawing in this ugly vector again, I'm going to draw in its pretty components. So our pretty components are f sub g y, meaning f sub g new y, and this guy here is f sub g x, meaning f sub g new x. And I have the values for some of those things. All right, so from here, I think in the interest of not making this problem, this video too long, and because the rest of this is actually back to normal in how we do this, I'm just going to give you kind of the short version. I'm not actually going to solve the whole thing, basically. So from here, what would you do? Also, it won't fit on this stupid Jamboard. You would do step 3 on the y side, f equals ma, but really it's sigma f sub y with a hat is equal to ma sub y with a hat. And the y in this case is new y. So a sub y, how quickly is Denise accelerating in the new y direction? She isn't. She isn't flying off of the hill. She isn't flying into the hill. So this one, of course, is 0, which means the whole right side is going to be 0. Sigma f sub y is going to become, grab your forces in the new y direction. That's going to give you f sub n with a hat plus f sub gy with a hat. And you know what? I changed my mind. I'm just going to do the whole thing. I'll have to write small to squeeze it in, but yeah, I might as well do the whole thing. All right. From here, what do? You do step 4 on the a side. Take the hats off. F sub n is in positive new y direction, so that gets a positive. F sub gy, well, that's in the new negative y direction. That's in the negative new y direction. It's down-ish. So that gets a negative. So minus f sub gy. And this is equal to 0, which means f sub n is equal to f sub gy. And we actually already know that number. You don't have to do these steps in the exact same order, but, we've already solved for this. I have that number over here. So f sub n is equal to 481.66 newtons. Yeah, this is what I got up there, so that's cool. Kept an extra sig fig this time for some reason. Silly me. But anyhow, yeah, we solved for the right thing. Gave it the right units. That's a reasonable number. So you give it a check. On to the other side. On to the x side. Which color? I got black. Okay, so on the x side, I'm starting up here. All right, you'll know which part is which. Step 3b. F equals ma, but really, sigma f sub x with a hat is equal to ma sub x with a hat. We can assume that Denise is accelerating in this new x direction. So for now, the right side of this is going to remain ma sub x with a hat. Be an x, please. The left side, sigma f sub x. All right, grab your new x direction forces. You will get f sub k with a hat plus f sub gx with a hat. On to, I guess I got blue again. On to step 4 on the x side. Take off the hats, put in the signs. F sub k, that is in the negative new x direction. So yeah, it's back up and to the left. So that one is getting a minus sign. So minus f sub k. F sub gx is in the positive new x direction. So that gets a plus. Equals ma sub x. Okay, we're going to assume that Denise is in fact accelerating in this direction. So this is the positive new x direction. What that means is when I take the hat off of this, it gets a plus. So the right side is ma sub x. The thing we're trying to solve for is her acceleration in this direction, a sub x. So we're going to divide both sides by m. M's will cancel on the right side. I'm going to rewrite this, switching left and right. This is going to give me a sub x is equal to minus f sub k plus f sub gx, all of this over m. And then from here, yeah, this is kind of normal. F sub gx, I have that number. M, I have that number. F sub k, remember I've got to use this idea. F sub k is equal to mu sub k f sub n. So let me rewrite it in letters one more time. A sub x is going to be equal to, don't lose the minus sign, minus mu sub k f sub n plus f sub gx, all of this over m. So this is going to actually be equal to minus mu sub k is 0.150, that number from up here. F sub n is that number we solved for in part 1. I'm sorry. So we solved for on the A side. 481.66 newtons plus F sub gx. Okay, that is this number here. We did that back in step 0. 337.26 newtons. All of this gets divided by the mass. And the mass is 60 kilograms. And remember, you've got to get the order of operations right here. So one way you can do that is put a big parentheses around the entire numerator. And if you do that, whoop, sorry, typo. My numerator ends up being 265.011. Divide this by 60, and I end up with 4.41685, which rounds off to a sub x is equal to 4.4, rounded off to 2. It's an A in acceleration, so its units will be meters per second squared. Put a box around it. Grab the red pen. We wanted A in units of meters per second squared. That's what we got. It is A in the new x direction. Its units are meters per second squared. And now let's think of this value, 4.42 meters per second squared. Is that a reasonable acceleration for a skier? Well, it's not, it's somewhere between 0 and g. If Denise is skiing, she's not going to accelerate downhill as quickly as if she had fallen off of off of a cliff. So yeah, it makes sense that that number is somewhere between 0 and 9.8 meters per second squared. So I'm saying that makes sense. So yeah, tricky problem. Hopefully you found this video helpful.